control?
Oh, it's fine. That's fine.
It works. Okay. Let's wait for 2 minutes.
Okay. Hello. Okay.
Good. Okay, I think we can get started. So welcome to the IISE colloquium. Today we are very honored to have Professor Raed Kontar to visit us. So Raed is actually alumni for UW Madison. He graduated in 2018, and now he is assistant professor at the IOE department of University of Michigan. So after he graduated, he has an amazing career trajectory, and now he works mainly in the federated and decentralized probability modeling. And he has won several prestigious awards from like Best Paper Awards from Informs, QSR, data mining, and also IISE. And he recently also won the prestigious NSF Career Award. So let's welcome Raed for his talk today.
Yeah. Hello, everyone. Thank you for inviting me. First of all, I have to say that this is a very special seminar for me. I'm a graduate from here. I was just mentioning to Laura that my first time on a flight landed in Wisconsin, in Chicago. But then I drove here to Wisconsin, so this is a very special seminar to me. And my advisor is not here, unfortunately, but this is a picture in 2014 with my advisor, Professor Joe. So today my talk will be on, okay, I have a loud voice, so my talk today will be on federated data analytics, and it's partially inspired by a vision paper that we recently wrote with multiple faculty across multiple universities. It's called The Internet of Federated Things. We've created a YouTube channel as well for most of these topics that I will talk about on federated data analytics if you're interested to learn more about what I do. Okay. So for today's talk, I will talk a little bit about Internet of Things. What is the Internet of Federated Things? And I will talk a little bit about some of our recent efforts. I will discuss multiple efforts because my hope is to give you a snapshot about the opportunities that this area presents and the challenges as well. Okay. So what is Internet of Things? Actually, this is a slide that I used in my job talk in 2014. Internet of Things is basically a smart and a connected system. Okay. So what happened is we had our traditional systems, then we had this evolution in the sensor power, our ability to collect a lot of data, and our systems became connected. And really the hope of Internet of Things is to exploit the data to do smart decisions and move from a purely connected system to a smart and connected system. Okay? So here, what does connectivity mean? That data across multiple devices, let's assume cars on the road or your phones, are being shared or collected. Smartness is exploiting this data to do smart decisions, okay? By looking at the entire data and different components sharing their data with each other increasing their predictive power. And this notion of IoT is really a notion that dates back a long time ago when artisans used to come together to perfect their crafts. Okay? So this is a current IoT system, and this example is from, this is exactly what Ford, for example, and General Motors does. What they have is they have their systems. Ford has their Ford Sync system. GM has their GM OnStar system. And what happens is that data from cars on the road is uploaded in real time to some back processing office. And what these companies do is they analyze the data from those cars to keep the driver informed about the health of their vehicle. And in case there is an issue, to tell the driver, okay, you need to take some action. Okay? So our current IoT system is fundamentally based on three notions. A lot of data is being uploaded to the cloud. Models are learned in the cloud. And then these models are sent back to be deployed. But there are some obvious drawbacks of such an approach. The first drawback is we are collecting so much data these days. Just analyzing all this data in a central location is extremely time-consuming. It's energy-consuming. Learning a deep network with 1 billion data points consumes as much energy as doing a round trip, a 4-hour round trip in the US in a flight. And in reality, learning with all these big data is very inefficient. What we do typically is we filter out the data, we do some pre-processing before learning. Then the need to upload a lot of data comes with a communication burden. The need to store comes with a storage burden. The need to learn and send back the decisions to the edge comes with latency. Okay? And finally, definitely, there is privacy. Actually, a lot of people with GM didn't want to enroll in the OnStar system. They didn't want people knowing where they are at a specific location. So the fact that you are uploading your data is an infringement on privacy as well. But what is changing today? What is changing is that the computational power of our devices is increasing tremendously. Okay? We're seeing a Moore's law on the computational power. AI chips are infiltrating the market. You will rarely see right now a 3D printer without a Raspberry Pi attached to it. Raspberry Pi becomes $50. It's a small AI chip that can do a lot of computations. Tesla, I was just mentioning that Tesla's autopilot system has 150 million times more compute power than Apollo 11 on the car. This is more than 500 MacBook Pros computing power on the car itself. Okay? Smartphones now have computational capabilities comparable to everyday use laptops. Okay? And why is this important? Because this opens a new paradigm for analytics within IoT. The ability to have computing resources at the edge allows us to process more of our data where it is created at the edge. And this is really the underlying idea and the underlying motivation behind this talk, is how can we create models to move away from the cloud to the crowd, to process more of our data where it is created at the edge. And why is, first of all, I want to give this analogy to our body. This is how our brain works. We get a lot of external stimuli, but not all this external stimuli bombards our brain at once. We have intrinsic filtration systems, okay? The dendrites, the nucleus, filters the information before it sends it back to the brain. And actually, a lot of neurological disorders come from the inability to filter external stimuli. This is why some kind of processing more of your data at the edge is important. So let me give you just one example how things are being done nowadays. This is not the only potential approach, but consider a very simple system where you have phones, and then you have a central orchestrator that is trying to orchestrate the learning. Let's assume a very simple situation. Let's assume the central orchestrator wants to learn an average, just the mean, okay? So in current IoT, each device will send out their feature vector, and then the orchestrator will just compute an average. But if each device has some computing capabilities, and they are able to compute their average locally, then that average is a sufficient statistic to calculate the global average. As such, you do not need to share your entire data vector. You just need to share an average to be able to calculate a global average. In reality, models are much more complicated. They cannot be solved in one shot. You need multiple communications between an orchestrator and edge devices. They need to talk to each other multiple times to solve a specific model. I should say a disclaimer here is that this is not the only possible approach. for a distributed system where you have a central server. It might be the system where decentralization, where phones directly talk to each other, but this is just one possibility. So why is this Internet of Federated Things important? First of all, privacy. If you have computational power at the edge, you do not need anymore to share your raw data. You just share whatever you learned. The second thing is computation and energy. By exploiting computational power at the edge, you don't anymore fit large models, but rather massive parallelization becomes a reality. And actually, interestingly, if you have an Android 13 phone, you will find in the first week, your phone will be very slow. And the reason is that Google right now is doing some model learning on the phone itself, okay? They are trying to do this decentralization, and some of the models, like the next word prediction, after you buy the phone and activate it, are being learned locally, okay? And basically, they're making money. They're using your compute resources to do the processing. Cost. Less information is transmitted to the cloud, less bandwidth is consumed, and less storage costs. Fast alerts and decisions. If you have a local model, you can do your decisions locally. You do not need for someone to send out your model to be able to do decisions. Fast encryption, this is an obvious advantage. If you're just sending out summary statistics, it's much easier to encrypt summary statistics compared to encrypting entire data sets. Resilience as well is an often, because you do not rely on just one central cloud to whether it fails or not. Diversity and fairness, I was just mentioning this example. Hospitals, for example, have this HIPAA Act where two hospitals cannot collaborate with each other to learn a model, but with decentralized, federated, or distributed analytics, they can do so without actually sharing the data. So there is a lot of benefit to be extracted from such a system. And I should mention one thing is this notion of federated data analytics is fundamentally different than distributed learning that we usually hear of. What is distributed learning? Distributed learning is a centralized system where the clients are compute nodes, like GPUs, okay? And distributed learning follows this philosophy of divide and conquer. So basically, I divide the data across compute nodes, then I conquer, I aggregate statistics to learn something. But in a federated sense, in the Internet of Federated Things, first of all, there is nothing to divide. The data is already partitioned. It's at the edge. You do not have the luxury to shuffle, randomize, or divide the data. It's already with each component, with each client, with each phone, with each user, with each car. There is nothing also to conquer. Your goal is to improve the power of each device to learn, to control, to predict. You're not just learning one thing that fits everyone, okay? So this is a fundamental difference that raises a lot of concerns and challenges. Here I want to say that the industry in the past 2 years has seen some applications for federated and decentralized inference. But the efforts are really in their infancy phase. Everything that was done has been done just to learn a predictive model using first-order methods. A lot of questions need to be asked. And actually, the applications themselves will dictate the challenges. So I do envision this is an area with a lot of potential challenges. So today, I will talk a little bit about two of the challenges, how we solve them, and then eventually I'll shed light on other challenges. The first challenge is more machine learning type of a heuristic approach. The second one is more ground in theory, okay? So let's start with the first topic, is called a personalized federated learning via domain adaptation with application to distributed manufacturing. This is a paper with my student. So currently, most of the work that has been done in mobile applications is focused on fitting a global model. So we have data at the edge, we have a central orchestrator, and we're trying to learn one model that fits them all, one big global model. So mathematically speaking, you can think about this model. I'm trying to learn some mapping, f of w, parameterized by w, be it a neural network, being a regression, you name it. And I'm trying to minimize some empirical risk function, okay? So the empirical risk function is defined as the average risk or a weighted risk over each client's risk. So each client has the risk function, and I'm taking their weighted sum, okay? And as we know from statistics, an empirical risk function is just the expectation of the data over some loss function. Squared loss, if you're using deep learning, it may be cross-entropy loss. So the goal is really to learn this f of w, okay, which is a global map that we are trying to learn, okay? But the difference in this Internet of Federated Things is that client I can only evaluate their own risk function, okay? And the central server, the orchestrator, does not have access to the data sets. So how to solve this problem? Actually, the approach, the general framework to solve this problem is very simple. You have two functions. You start with an initial model, let's say WT. You send this model to the clients. Then each client does their own update, okay? They update WT based on their own local data, a W that minimizes their local risk, okay? They send it back, and then there is the orchestrator update. The orchestrator gets the updates from all the devices, then aggregates them in some form. And actually, this is just basically the very simple framework. The client does an update, the orchestrator does an update, okay? The very first, very simple paper that really brought this federated learning field and deep neural networks into attention was a very simple model called Federated Averaging, and we've known this model for a while under distributed SGD. The idea is very simple. Each client just does stochastic gradient descent, takes batches, does descent, and then the orchestrator update is just an average. Just take an average, a weighted average, weighted by the data, just an average, basically, okay? And this model in deep networks was very powerful. Even till this day, it showed very nice results. It showed very good results on many different applications. And people have been experimenting, adding to it, adding some steps, whether on the client update, doing some regularized first order methods, maybe jumping into second order methods, some different ways to aggregate, okay? But in engineering systems, there is usually a challenge there. In engineering systems, sometimes we cannot learn one model that fits all. And the reason is there is a lot of heterogeneity across clients, okay? Imagine cars on the roads. Different people operate cars in a different manner, so the operational, the environmental factors are very different. In such situation, we really need to learn models that are personalized, okay? That are tailored to each specific client. And fundamentally, on the more mathematical side, one can directly notice that if you have the optimal solution for each client's risk, okay, does not align with the optimal solution of the global risk, okay? It doesn't. This only aligns if we have infinite data, okay, locally, okay? And this phenomenon is called client drift, and indeed, a lot of work has shown that when there is a lot of heterogeneity in the data, one model that fits all will not work, okay? You can think about the client drift as such. I think optimization folks here know that in distributed SGD, which was proposed a while ago, you do one step, you take an average. You do one step, you take an average. So the expectation of this one step is just basically much like taking the average of the gradients. But if you do multiple steps, then take the average, then you have an issue. You have an issue there because each client can go in their own direction, okay? And an average might fail, okay? So personalized modeling is important because in engineering systems, we have different clients operating under different conditions. So there has been some approaches to handle personalization. What are those approaches? The main model to handle the personalization is to assume, okay, let's assume that each client also has a personalized parameter, theta I, okay? So the clients are collaborating to learn a set of global parameters, W, and a set of personalized parameters, theta I. And here people do it in two ways. The first way is weight sharing. It's a very simple idea. And it's very specific to a neural network. They assume, okay, I have a big neural network. Let me divide this neural network into two stages. The first layers are shared across all components. And the last layers are more local. And we all collaborate to just learn the first part, which is the global component, okay? And then we do averages to learn the global component, and then each one personalizes. The second approach is what we call a trained and personalized approach. What is a trained and personalized approach? We all collaborate to learn a global model, one model that fits all. Then we said, okay, well, then we say, okay, let each client take this model and fine-tune, but make sure you are close to the global model. So this is a way to somehow balance between the information that you learned globally and the local information. They ask the clients, okay, fine-tune, use your own risk function to update theta I, but make sure somehow you are close, or encourage the parameter to be close to the learned global model. And there are different regularization ways to achieve that. But let's take a simple counterexample. Let's assume the functions are generated from a sine function with just a phase shift, sine 2 pi x plus ui, and assume that ui is a uniform on 0, 1. Okay? Here then, if you have this function, those are common in vibration signals. We have those sinusoidal signals with the phase shift. And let's assume we're trying to minimize the population risk. Here, f is a functional on 0, 1. Okay? Using some algebra, it's pretty simple actually, one can prove that the population risk, this is a population, not an empirical risk, the unique minimizer is a function that always predicts 0 when minimizing this average risk over all clients. It's a function that predicts 0 for every x in 0, 1. So basically, it's any parameter, and neural networks can always find parameters that achieve this. It's any parameter that predicts the overall function as 0. And that means you are learning a very bad global model. And what's worse is you're asking your model, okay, make sure, or I encourage you to be close to a very bad model. This exacerbates the problem when you are doing trained and personalized. Okay? So this first work that we do, we try to address this problem. And the first question is we ask, why is this problem happening? This problem happening simply because heterogeneity can be defined from two different perspectives. Heterogeneity is a heterogeneity in the conditional distribution of y given x and the marginal. Okay, what does that mean? That means y given x models the change in the input-output relationship, but you can also have a change in the input across different clients. This situation, the models that we are doing, this model where you have f theta of I, only handles one thing, only handles the change in the input and the output relationship. So the question that begs itself, how can we model a situation where how can we model heterogeneity while modeling both the conditional and the marginal? Okay? And our approach to this problem is rather simple. Okay? We suggest a way called domain adaptation. What is domain adaptation? Our idea is the following. Let us learn a function that takes the input and maps them to some space. Hopefully, this space will be domain invariant. Hopefully, this space will control the change in the marginals. And then let's learn a mapping that maps back, okay, to the output space. Okay, so you can think about theta to be an encoder and G to be a decoder. But the problem is this model is fully personalized. If you learn this model, basically you're learning a model for each individual client alone, because beta I is personalized for the model, gamma I is also personalized. So how do we share data in such a model? How can we make sure that the parameters beta I will lead us to go, not make sure, encourage them to go into a domain invariant space? Okay. What we do is we design a bi-level optimization approach. Okay. The bi-level optimization approach is just a minimization gamma I of f tilde under the constraint that W beta I are the minimizers of the weighted empirical risk. Okay, let me just try to take each part alone. Okay, for learning the decoder G of W, what do we assume? We introduce this dummy variable W, and we say, okay, I want to learn a model that minimizes this risk, GW. I want all my inputs, want my all inputs in the feature space to be mapped by just one parameter, W. So basically, how do I encourage here domain invariant features? I have a single mapping W, GW, that maps all the feature space back to the output. And this encourages all the clients to somehow extract features that are in a domain invariant system. Okay? Then, after I have aligned the clients in the same feature space, I say, okay, right now personalize. Right now, given this W that I learned, learn a personalized decoder that is close to W. Okay? This is done in a bi-level optimization perspective. So basically, we have beta I and beta I, the encoder, and W is the global component, are updated using the gradient of the lower level of the bi-level optimization. And then gamma I are updated on the upper level of the optimization. Then we take averages. So the only thing that you need to share here is just the parameters of this dummy variable, W, between clients. You just need to share W to learn the system. And under some theory, this is a very informal theory, we can recover some convergence. Actually, the parameters W and beta, this is just convergence to a stationary solution, converge at a rate log t to root t. And the parameter, the personalized parameter, gamma I converges at a slightly lower rate, which is t to the power 1/4. Here, I should note that actually in here in the rate, there is also a parameter that is rather important, which is E, which is how much you train locally. Specifically for the global variable W, it shows up as E squared. And what does that mean? That means if you train a lot locally, you may overfit on the local data set, okay? And this convergence rate becomes slower. So it's very important not to train a lot locally. So there is this compromise between how much you overfit to your own data and how many communication rounds you need. Because the more you overfit, you need more communication rounds to solve this problem. So we take a simple situation, we revisit the sine example, this exact sine example, and you see our model here, the feature space, it somehow aligns all the sine functions into a similar feature space. And then under this feature space, it tries to predict the sinusoidal functions. You can see here the prediction is done accurately for our model just by 1, 2, 3, 4, 5 points for each function. We have 3 sinusoidal functions, each having 5 points. Clearly, learning those individually without a parametric assumption is very hard. Here, we do not put any parametric assumptions, and we are able to learn the model in a nice way. Actually, one can prove that in this specific situation of the sine functions, that if alpha is a normal distribution, this should be squared, and theta I is uniform, with correct parameterizations, the global decoder will have an amplitude that is just the mean of all the amplitudes. So the global decoder, the dummy variable that we introduced, is somehow the center, okay, of all of the feature space, and then the mapping gamma I, or the amplitude that maps back, is the average of the individual amplitude and the center, much like the prior and posterior. This becomes like a prior, this becomes a posterior that uses the prior, but the amplitude that we learn is based on the function itself. So this can be solved in closed form if we correctly specify the model under the correct parametric assumptions. Here we do some testing with data sets that have feature differences, obviously, because one data set is a sketch, cartoon, art and painting, and we try to use them to learn each other better. So we learn a model across all of them, and clearly they have some domain problems. Here I just want to point out that at the University of Michigan, we are creating a prototype. It's already in place, needs some tweaking, where we have multiple 3D printers distributed through the university, and they are connected to a central server, and they're collecting data in real time, okay? So you can do experiments, and we test our model in this situation. And the printers are printing the exact same box. I was telling Jeff that I brought the printers, I assembled them, and if you screw the knot a little bit more, there will be differences, okay? And those actually are differences in the marginal and the input, okay? So this where the problem rose, and we tested our model in that situation. I want to say here that one possible use and one possible extension to this work is multitask learning. Here, everything that the ability to learn is all dependent on having this W, or having a global model. In all these models, in our model, in domain adaptation, in the global modeling, you start with the W, then you personalize. But the question is, can we use multitask learning? Can we avoid the need to have a W or to have a shared component? Can we just learn, extract knowledge collaboratively without having a global component? This may be a question. So the second topic I want to talk about is a bit different, but I just wanted to highlight some potential avenues for this new topic. It's called a personalized PCA, decoupling unique and shared features. The paper is right now on archive. Okay, this is more on the feature extraction side. Let me tell you the goal of this problem. The goal is simple. Actually, this is my student's cat, okay? And we have those 3 images, okay? Each image has a cat that is moving, and the goal for us is to somehow decouple. We have multiple data sets, and we want to decouple the shared and the unique features. This is the goal of this paper, okay? And as you can see, the global PCs, the PCs of the shared or on the central server, are PCs just the background, and the local PCs are just the cat that is walking. This is the cat in the back. This is the cat here. How do we do so? Okay, so this is called personalized PCA, and this is the goal, and it has applications. If I can find the local features, I can do clustering, I can do monitoring. A lot of questions can be asked, okay? So our model, let me start with our model. So our model divides the data into global components, R1 global components, and R2 local components, okay? We assume that the data is generated from R1 global components, okay? And the components are modeled by U. Theta are the basis functions, the coefficients, theta i's and phi. And then we have V, which models the local components, okay? And we have noise. We assume it here, sub-Gaussian noise. And the question is, can we decouple the global and shared features, okay? And the goal is, perhaps if we are able to decouple these features, we can learn some interpretable knowledge, okay? So this is an example that highlights homogeneous PCA and personalized PCA. In this situation, the data, we have 2 data sets that look like this. And if we bring them together and do some decomposition, some SVD, and learn the top 2 eigenvectors, you can see that there are the 2 eigenvectors. Somehow the first one is up. The second one is the average across the 2 data sets, okay? In our situation, what we want to do is we want to learn the global component, which is the black one, and we want to learn the 2 different PCs that model each individual data set, okay? So how can we do that? Let's start with a simple formulation. Here we formulate it from a covariance matrix perspective. Let's first of all write things in matrix form. We assume U are the global components, Vi are the local components, local PCs, and Yi are my data sets, the matrices here, okay? And basically, if we want to model this, our objective is just to minimize the trace. This is the formulation of PCA. But we want to minimize the trace of U transpose SU. S is the empirical covariance matrix. The trace of V transpose SVI. This is the local clients, local components. But here is the trick. In PC, we know that U should be orthogonal. The PCs should be orthonormal. The local components are also assumed orthonormal. But the trick that we add is very simple. We just ask that the model, I want my local components and the global components to be orthogonal, okay? And SI is the data covariance matrix. Clearly, those constraints are non-convex, so the question that one begs to ask is this model identifiable? Is it learnable? This is the first question. We know from the Eckart-Young theorem that in general, in PCA, if I'm just doing a PCA over a covariance matrix S, this model is identifiable. And if you limit the rank to be R, then basically the solution spans the top R eigenvectors, the top R eigenspace of S. We know this theorem for a while, and basically we do SVD, we find the top 2 eigenvectors if that satisfy my rank constraint, okay? But this doesn't apply in our case, simply because, just give a simple example, if all clients have the same images, they have the same global and unique features, we cannot tell the difference between global and unique features. So this model in general is not identifiable. So new conditions are needed, okay? So what is this condition? We find a very simple identifiability condition. Consider pi I is the projection on the subspace spanned by the local components, by the true local components, okay? So the identifiability condition here, okay, is that the maximum eigenvalue of the product of the average over the product of the local subspace projections is less than 1 minus theta. Is less than or equal 1 minus theta. What does that mean? I want my local subspaces to be a bit different. Okay? There should be some differences for me to be able to identify this model, and clearly, clearly the maximum eigenvalue of pi I is 1. So in this situation, this value is bounded between 0 and 1. So theta is between 0 and 1. Okay? So theta measures the subspace differences, the differences in the local principal components of each vector. And we need to have some differences to be able to identify the model. Okay? And this is a very informal theorem. A very informal theorem here. Pu is the projection of the column space of the global components. And we indeed show that if we have, under some identifiability conditions, if the eigengaps are delta, the eigengap is the gap between the where you cut and the next one in the principal components. This model is identifiable, and interestingly, it becomes more identifiable as theta increases, in the sense there is more heterogeneity. So the more theta is, there is more heterogeneity. This model is identifiable with high probability, with probability at least 1 minus delta hat. Okay? We'll not go a little more into the details of the theory, but the next question is, okay, we know this model is identifiable. We identified the identifiability conditions. The next question is how to solve it. Okay? So we're solving with orthonormal constraints and orthogonality constraints. So one possible approach is to do Stifle gradient descent. So look at the manifold. We look at the Stifle manifold. The Stifle manifold is formed by all orthonormal matrices. And then we can do on the client side a Stifle gradient descent. But just a fast note, the Stifle gradient descent takes the gradient, projects the gradient on the tangent bundle, okay, to the tangent space, then does decrease using that projection. Okay, so basically, some people usually call it the parallel descent. It is doing descent on the tangent space. So this is the projection to the tangent space, and clearly the derivatives, the gradient with respect to u is the gradient with respect to u is SV. The gradient with respect to those are the gradients here, just the gradients of the objective. Here, take the gradient. Obviously, it's UV for the first one, SU and SV. Okay, and then we aggregate them. So this is a potential problem, a potential solution, and then we aggregate the solutions. But there is a key challenge here. We aggregate them by taking the average. The key challenge is that when you take the average, okay, so you have the global components from each component, but the global components need to be aggregated. Let's take a simple aggregation, just taking the averages. So the averages and the local components are not feasible anymore. They're not orthogonal. So how to solve this problem? To solve this problem, we do a correction step. So at each client, we do some kind of a Gram-Schmidt orthogonalization. So what we do is we project the learned global component U, okay, into the we project V onto the column space of U, and then deflate V, okay? And in this situation, it's just Gram-Schmidt orthogonalization. Things become orthogonal. And actually, interestingly, this point, it's important to know that after doing this orthogonalization and taking the average, you're not on the Stifle manifold anymore. This is not an orthonormal matrix, but you can show that you are close enough. Okay? So the next question is, how do we bring it to the Stifle manifold after doing orthogonalization? And here, this is a bit, needs a lot of mathematical explanation, but we introduce a notion called generalized retraction. So retraction in the literature is a retraction from the tangent space to the Stifle manifold, okay? A generalized retraction, we define it as a retraction from any R matrix RD by R to the Stifle manifold. It's a retraction that preserves the column space. So if you retract this matrix that is orthogonal to the other, it preserves the orthogonality. And the second thing, it is close to projection to the tangent space. So this closeness is modeled here. So you can think yourself, if your point is already on the tangent bundle, okay, then this becomes just this part, which is the definition of retraction. So think about it as two things. It's the retraction from any matrix to the Stifle manifold. The conditions is it preserves column space. It's close to the tangent space, okay? And actually one can show that the polar projection is indeed a generalized retraction, okay? QR decomposition is also a generalized retraction. And as such, in this situation, if we retract this orthogonalization, we get a new V, okay? And this V maintains the orthogonality of V and U. At the same time, it lies on the Stifle manifold, okay? We also do this for the averaging step. I will not go a lot into the math, but the algorithm basically turns out to be the following. You start with feasible global components and local components. You send the global component to the client. The client corrects the global component, then does descent, okay? Then afterwards, the client does descent to update U and V. Then the server just takes the averages and retracts them to a feasible space, okay? So what's happening here is just 3 steps. You start with the global component. You send it to the clients. The clients do their updates. They send back their updated global component. You take the average. That's it. So basically, fundamentally, to learn this model, if you are in a federated universe, you can have a central server, and the only thing that you need to share from client to client is the global component, is your local global component, okay? So we show here that, actually, interestingly, this algorithm, despite complications, definitions of generalized retractions, this algorithm is convergent, and not only convergent, if you initialize close to the solution, okay, you can recover the true solution exponentially, okay? And the interesting here is theta. Theta, as we have more heterogeneity, this model is faster. We know in federated learning, in general, the notion is that as more heterogeneity, convergence is slower. Convergence will be affected. The model will not be generalizable. This is the complete opposite here. The more heterogeneity we have, the better the model is. So here, actually, this is very informal. There is a noise term because we assume that the noise is sub-Gaussian, so it is sigma to the power 4 here is the noise, okay? Let's take a very simple example. I'm not sure any one of you, if you know robust PCA. Robust PCA is a very famous model of PCA that was proposed a while ago, and it aims to find sparse components. So it aims to find a low-rank approximation of a matrix plus a sparse component, okay? Under what we call incongruency assumptions, where the sparseness is somehow spread out. So let's assume there are 4 images. This is just with 4 images, done. We have 4 images. Those were done on PowerPoint, triangle, circle, X, and cloud. And we are trying just to extract the local features, just from 4 images. Sparse PCA cannot do anything with 4 images, even with many images, because those are not low-rank components. Those are not sparse components, okay? Our model with 4 images was able to identify the triangle, the circle, the X, and the cloud. This is just the local PCs. The background is just a solid background, okay? So we use this approach for image segmentation, and this is this is going back to the example I showed you. Another example that I want to highlight, which I thought was interesting, we did that, is we looked at the presidential debates from the past, since 1960. So we have presidential debates each year. It's a text, okay? And it's assumed that each year is a data set. And our goal is to find the words that somehow, the global components, the words that were used commonly across all the years, and the words that are unique to each year in the presidential debates. And we found interesting personalization tools. Here are the personalized or the local components. For example, in 1988, where there was a drug problem, the presidential debates focused a lot on drug, strong future enforcement. In 2008, when there was the war in Iraq, it focused on Iraq, Afghanistan, Pakistan, Iran. Recently, the focus is on Trump, Hillary, taxes, etc. So what the goal here is, what do we do? We have different texts. We try to find the common components across the text or the common features, and what is unique to each text, okay? So this is just one example on how did this modeling to extract some useful information, perhaps. I want to just shed light a little bit on different areas. Again, I would love to have focus on one, but since this is a very new topic in our field, I just want to highlight the possibilities that one can look at. The first possibility here is hierarchical modeling. We still do not know how to do a hypothesis test, how to fit a linear model. In linear models, do we really need to do the heuristics in deep learning, taking averages or as such? How can we do hypothesis testing? How can we learn a linear model, how to do variable selection? And our solution to that was via some hierarchical modeling where we assume that somehow all the clients' datas or parameters are generated from one global distribution. And then we do hierarchical models to quantify uncertainty. Another thing is, the question is, can we distribute learning when we have correlations, when data are correlated within and across clients? And the question that we asked is, how can we do a distributed inference for a Gaussian process? And learning a Gaussian process in a distributed fashion is very interesting. Why? Because the Gaussian process learns a prior on the data. So what does a prior mean? If you have a new data set, you can just use that prior, condition on it, and do predictions. So somehow you're learning a good starting point for any new data set, for any car that enters your system, for any phone that enters your system. You learn a good initialization. Another question that we asked is fairness. Obviously, when you have heterogeneity, different clients can have different performance. Some clients will be fitted by the model extremely well, some clients not. How can we somehow encourage uniform performance? We want to encourage that all clients somehow perform with small variance in their predictive accuracy. How can we do that? And in this model, we just basically penalize the spread of the group losses of different clients. Here, groups can be clients of different ethnicities, or if you're looking at individual fairness, each group can be one client. We want to say that the loss of each client, the loss function, are somehow close to each other. And it turns out that this formulation is basically is basically reweighting the clients based on the statistical ordering of their losses. So it's a client reweighting, much like you take an average over the empirical loss, you define a weight here, and this weight is dynamically, automatically updated based on the statistical ordering of the client losses. So those are just some possibilities, but I want to end by saying that I envision that as this Internet of Federated Things infiltrate more industries, the applications will dictate the challenges. And here I say, only with a deep engineering understanding of the underlying system and domain, one formulates the right analytics, okay? And as such, since there are practically non-distributed analytics data sets, what we have done is we created a public directory at the University of Michigan where you can go and find data sets, engineering data sets, real-life engineering data sets to test the developed models upon, okay? So some of the applications that I would expect will be of high relevance is decentralized or distributed control of the grid system, of the control of traffic control. In manufacturing, there is a lot of democratization and distributed manufacturing already happening. So I envision a lot of applications, and it's a ripe area. There's a lot of open questions, and a lot of challenges that need to be resolved. Here I want to show one thing that also an experiment that we are doing using the data set that we have at Michigan is we're doing what we call distributed design of experiments. Okay? What does that mean? You can think about it. If you're doing trial and error, usually in many systems, we want to find the optimal parameters or to find the optimal process. We do a lot of trial and error. We ask, okay, let me choose this point and do a test here. Let me choose this point and do a test here. And then eventually, I somehow slowly converge to a good solution. Okay, the definition here of good is rather vague, but what if I have different entities and they can all do trial and error? Can they collaborate to efficiently talk to each other to optimize the trial and error process? Can they use some kind of mechanisms to somehow collaboratively decide what should be the next experiment, what should be the next treatment, so that somehow I am collaboratively, as a group, we are able to reach to the optimal solution much better, much faster, okay? So those are just some topics to highlight this area. I hope I was able to convince you a little bit that this is an interesting area. It has some potential, and hopefully, with the increase of edge computing power, with the decrease of the prices of AI chips. Actually, the problem with AI chips nowadays is not only that there was a problem in the company. There is a lot of the company that produces them. There is a lot of demand. With the increased demand for AI chips, with the decreased cost, with the increased computational power at the edge, there is a lot of leeway to distribute, to federate, to decentralize. Those all words may mean the same thing, our analytics. And thank you.
Okay, I think we have a couple of minutes for Q&A. Any questions for Raed?
Yes.
So I would like to ask, for the personalized use formulation, you told that local and the global components have to be orthogonal, but like
Orthogonal.
yeah, while they make sense like in modeling terms, like those, but like what is the use case behind that? Why the local and global components should be orthogonal?
Okay. The goal is as such. I want my global and local components to model different information. I do not want them to model the same thing. So there is one shared global component. There are different local features. I want to make sure that my local features model whatever my global components are not. And this is enforced using this orthogonality constraint between VI, the local components at client I, and the global component, the aggregated global component U. Please go ahead.
So regarding like the first work that you do like about domain analysis, in that like how far the domains can be. Suppose like if I have some sensors on automobiles that run on roads, versus if I have some sensors on probably like aircraft or stuff, like how far can the domains be?
That's a good question. The simple answer, they can be as far as you want, but you will learn nothing. Because if they're very far away, if there is nothing to learn together, there is no need to do this collaborative learning process. Okay? You can model it, you can get an answer, but this answer will not generalize well. So the goal here is you need to believe there is some commonalities in the domains. So for example, the example I gave you here is that you're modeling the exact same thing. You can see here, you're modeling horses and dogs, but different cartoonish, you know. Somehow the belief that we have is that we extract features in the same space. The features of the same entities will be somehow close to each other in some space. Okay. Because the goal is to borrow strength.
Any other questions?
I can just yell. So I didn't quite understand intuition about, you were talking about using something having to do with an eigenvalue to measure the difference between subspaces. Like I've only ever seen, that doesn't seem intuitive to actually do that measure. I mean, I would think you measure the angle, the principal angle between subspaces. That's what I've seen before in that type of literature.
So you're So this one here?
Yeah.
So the maximum eigenvalue? Okay, so you can think about what is pi? What is pi? Pi here is VI, V transpose, okay? So this is the projection matrix, okay? So the projection matrix, we're just multiplying the projection matrices, okay? So in this situation, if the projection matrices are pretty much the same, this will be 0. You can think about it in this way. Because the maximum eigenvector, you can look at this inequality. This inequality, this is the lambda max of 1 over n, the average projection matrices at local client I. Okay? So this is bounded by 1 over n, the summation of the lambda max of each projection matrix. The lambda max of each projection matrix here is 1. Okay? So if the projection matrices are not the same, okay, this number, the theta, will be large.
So actually, I have a question for this personalized PCA. Have you tried, I just think about how difficult the problem is from the motivation exam. Have you tried using some kind of like a sparse PCA? First can decompose global components and those sparse anomaly. And then the global components, even though you don't need to even consider shared learning, you just each individually decompose global components. And then after you decompose global components, you try to somehow look at all the individual PCA results and then try to aggregate the global components. Will that be like an easier step, like approach to solve this kind of personalized PCA?
Let me answer. This is a complex question, and we're working on it. But sparse PCA basically is a robust PCA. Do you mean robust PCA? Because a robust PCA assumes that we have a matrix Y, and it is modeled as a low-rank component, sigma, plus sparse noise. Okay? So this is a robust PCA. This is what we do. Robust PCA, what does it assume? Assumes that perhaps the unique component across all clients is sparse. Okay? So sir, there is some sparsity across different components. If you're modeling them by noise, there is sparse. But the problem is, what if the unique component at each client is not sparse? It doesn't need to be sparse noise, for example. It can be in this situation. This is an exact example here. Your unique component is not really sparse. Okay? But what we are considering is actually an extension here. We are trying to extend right now the model that we have in this situation, okay, to assume that there is some sparse noise. So to assume that there is some noise, the models are generated. The noise here is not just random noise. There is some noise, but there is some sparsity structure. But the problem, identifiability, becomes very challenging. Why? Because in robust PCA, why is it identifiable? Because sparsity there is the incongruency assumption. Sparsity is somehow scattered well, okay? But in this situation, we need to combine the identifiability on the orthogonality of the components and the sparsity pattern, okay? And the incongruency assumption. So this is something we are working on, but it is not that easy. But to answer your question, if simply the unique part is not sparse, your approach will fail, perhaps. But because we tried, this is an example, exactly, this is sparse PCA. This is an exact example of sparse PCA. Also, robust PCA is known to require a lot of data. And here our model regularization is helping the model that we have. Because we do not have a lot of data, we're putting the constraints that there is differences, and it's helping here. We just have 4 data points. This situation, we just have 4 data sets. This one is around 400 by 400. That's it. And we are able to learn this. This is robust PCA will never work in those dimensions. But this is exactly sparse because the unique components are not sparse. The robust PCA learns.
So in this case, the global components look like what? I'm just curious.
It's just the background, because you can think about something like this at the back.
So regarding the first work, the domain adaptation, you assume there is a shared W. My question is, how do you know define the dimension of the W, or like the case I mentioned, if there is like no shared W, how could you detect it? Will the model be overfitting? Yeah. Try to find some W, just try to explain the data, or it can automatically tell there is no such good global space transition exists.
Yeah, that's a good point.
Yeah.
So but first I need to emphasize something. W here is just a dummy variable. Why do we use it? Why do we use W here? Because how can I map the input into a domain invariant space? It's very challenging, but I tell the model, okay, make sure that all the inputs, all the mapped features, okay, can be mapped back using one single parameter. This parameter, the dimension of this parameter, okay, is the same as dimension as gamma, the same as the dimension of the decoder. But because there is one parameter that needs to map everything, so everything is encouraged to be mapped to a domain invariant space. This is what domain adaptation actually, fundamentally, when it was proposed, does. Okay? So this is like a dummy variable that we play with. But let me answer your question. Definitely, this model will excel when? If actually the the generative function, the generative data model, is in itself a composite function. So if the generative data function here is a composite function, okay, this model will excel. And to give you this example in this situation, if you have the correct specifications, and by correct specifications, I mean that your encoder is just a linear function, x plus theta, and your decoder is a sinusoidal function, okay? In this situation, if you learn this model exactly, what you will recover is that the encoder is mu a, has the average amplitudes over all clients, mu a. And that the decoder, the amplitude of the decoder is a weighted sum of the alpha I and the mean, okay? But this is under correct parametric assumptions. But one may think, okay, neural networks will capture those functional families easily, but of course you can overfit as well. So to answer the question, definitely if the model is generated as we model the data, this is the best situation. But since W is just a trick that we play on the model to map things into in the same dimension, this has a lot of application. This may work given what we tested on. Yeah. But this is definitely more on the heuristic side. Yeah. The convergence is just convergence is the objective function to a stationary solution. Yes. So I see. Okay. Okay. So let me just answer for this domain. You're talking about this theorem? In the domain adaptation or the PCA? Because in the PCA, it is the situation where higher heterogeneity is beneficial. But here, in just the model here, higher heterogeneity is not beneficial. Actually, if you model heterogeneity as a parameter, okay, you will see this parameter in the numerator. The PCA, but the PCA, okay. You're talking about which global? You're talking about the global parameter U. What's W here? Yeah, so here in W of theta maybe. So you can see here where theta appears. This situation, you can see from here, okay? So the more heterogeneity you have, the faster convergence. Maybe I didn't understand your question. Maybe I'll talk to you a little bit offline about it more. Sorry, I didn't understand.
Okay, so the right time for
Thank you.